All right. Welcome to United Astronomy Clubs of New Jersey. We are back here on site in Jenny Jump State Park in Hope, New Jersey. So, while we have people here wandering down and finding a seat before the show, I want to thank everyone who has joined us not only here, but also online, because that is right. We are live streaming these presentations live on Twitch and YouTube. So if you ever can't make it out or are just looking for something to watch on a Saturday night, you can also join us from the comfort of your own home. Say hi in chat because I do enjoy actually interacting with people there. Um, you can also check us out on our website. That's where you're going to find out a list of all of our upcoming presentations, our past presentations, also information on all our telescopes and our member clubs, because we are a club made up of other clubs. And as such, we try and get people in touch with their local astronomy club to bring the joy and outreach of astronomy and science. You can also check us out on our social media pages, our Facebook, our Instagram. We have a Discord channel where you can also ask all your questions and share your astrophotography photos. And so, with that, we're going to go over the safety briefing for some of the people here. So, if you need to use the bathroom, that is the porta potty in back. It's illuminated by red, although you can't see it right now because it's too light. You will definitely see it when it gets dark, which is why it's illuminated in red. We also have a little museum area and gift shop, which I will be manning after the presentation because still they refuse to give me the technology to be in two places at once. Once they do, I'm taking over everything. Not really, that sounds like too much effort. Each of the when you came in, each of the sheds you saw with the roll-off roof houses its own telescope. We have volunteers. Everyone here you see here is in fact a volunteer. We do not get paid. And all your donations and whatnot do go to helping us pay the bills and keeping this going and outreach free. But each of those sheds contains a telescope. So if you find one of our volunteers, most of them will, or many of them will be at a telescope. You can ask them what they're viewing tonight through their telescope. Or if you have a specific target in mind, you can also try and ask them if they can get that in the telescope site tonight. When we go to leave, we are using our headlights. We don't want to get run over. We don't want other people getting run over. We don't want to do the paperwork for people getting run over. So do that. Any flashlights when it finally gets dark, do keep those pointed towards the ground, though, because nothing's more annoying than having a random flashlight just spinning around. With that, our talk tonight is Anatomy of a Star. That's the correct one, right?
Anatomy of a Star.
Okay. He does a couple, Paul here, Paul Fischer, does a couple of our talks, Anatomy of the Star being one of them. He has a Bachelor in Engineering and Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in the sky, Paul's official start in amateur astronomy was several years ago, lying in awkward cold positions on a roof, where he caught the brief move. My tongue got wrapped around my eye tooth, couldn't see where I was talking. He caught a brief, clear glimpse of the Galilean moons of Jupiter, and since he's been here, we've trapped him. We keep him in the basement here at UACNJ, but he's also an active member of Northwest Jersey Amateur Astronomers. And with that, here is Paul.
Thank you, Kim. Hello, everybody. Good to, you picked the perfect night to be here. Look at that sky. That's not very frequent that we've seen that this season so far. So consider yourselves very lucky. And I apologize for delaying your gratification by looking through the telescopes by presenting this Anatomy of a Star. But hopefully it's useful for you and you'll get some information from it tonight. As Kim said, that I am Paul Fischer. I am a member of NWJAA, which is a local club not too far north of here, and an observer here at UACNJ. All right, before we begin, who, what, and why. So an introductory slide about why we're talking, who's talking, and why we're doing these. What we're hoping to what I'm hoping to accomplish with this talk. For any correct information, these are these are the two information sources that I developed my presentation from. Kenneth Lang, The Life and Death of Stars, Cambridge University Press, and Alex Filipenko, who is a professor, and Understanding the Universe, An Introduction to Astronomy through the Great Courses. It's a multi-DVD thing that I have. I'm sure some of that type of stuff is available online nowadays, but my particular copy's DVD. Highly recommend both of those, and that's where I got all the correct information. And if I misspeak or tell something wrong, that's not a reflection on those two people. That's a reflection on me. I just got it wrong, so you can blame me for any misinformation. So what are we going to cover tonight? We're going to introduce a particular star, give you the inside scoop about that star, the origin story of the star, and what makes a star tick. And then finally we're going to talk about how does the chosen star compare to other stars. And of course, not only does every star have an origin, but also every star has a end of the story. And I was trying to draw a comparison between, say, a Hollywood star and a astronomical star, and that's where that ended. I did not go anywhere with it. I apologize for not being creative enough to weave that throughout my presentation, but it was an attempt anyway. Introducing the sun. Okay, sort of. And why is that? Why is that the star that I picked? And there's a bunch of good reasons why the sun is a good model for us to use as an every star. So not only is our sun important to us particularly, but it's also a great model for us to have as an understanding of other stars throughout the cosmos. We do get asked this question, and some people don't always get it right. Yes, our sun is a star, and stars are the suns of other solar systems. Okay, so there is no major difference between our star and other stars. We just happen to call ours the sun. So that's just a name thing. Other stars could be considered the suns of their own planetary systems. However, we must be of two minds on this topic. When compared with data and measurements of other stars, the sun is really kind of average. In fact, I'll show you a diagram where you'll see it right there in the middle, where all the average stars lie. It's a very average star. However, our sun is also emotionally, historically, geologically, evolutionarily, and physically indispensable to us. That's why it's so important. That's why it's such an important thing to us. We wouldn't be here without it, and to us it's the most important star in the universe. So we have to think astronomically and scientifically, but also historically and psychologically. That did I cut out? Can you guys still hear me? Yeah, okay. We wouldn't be here without it. It is our most important star. And why is it sort of the sun? Why did I take this model that I'm going to use to describe how stars work and call it sort of the sun? Well, I like this phrase here. Astronomers are actually actuaries. Okay, so they take a statistical look at what is happening to stars and the rest of the universe, right? And the sun is only one star, where there are something like 300, 400 billion stars in our own galaxy. Other galaxies have trillions of stars, and then there's trillions of galaxies, so that's a whole heck of a lot of stars, right? So why is our sun sort of the model? The sun has been around, our sun has been around 4.6 billion years, and humans have only been around for 200,000. So what happens here is we have this conveniently located star that we can gather a lot of data from, but we also get to look back in time by looking further and further distances from ourselves. So we get the time sense and the development sense of other stars in our own galaxy and other galaxies that we compare to the detailed data we can get, the more detailed data we can get from the sun. And between those two things, we can combine them and come up with an better understanding of how all stars work. So it's a model in our heads, our understanding of stars. We don't get to see the entirety of the sun's existence, but we do by looking out into the cosmos and seeing various stars in various stages of development. We get to get that time sense by looking out into the cosmos, and so our model of how that works is actually a combination. Only have to take into account, I said that it's not a bug, it's a feature, right? So our ability to look out into the cosmos and see things as they happened, for instance, if a star, Proxima Centauri, is 4 light years away, we're seeing it 4 years ago, how it was 4 years ago. Our particular star is actually a very sun-like model. It's not a stretch to consider it in every star. All right, so let's start here. Hey, buddy, I said there would be pictures. There's pictures in these presentations. It's not all going to be boring text. It's one coming up, so here we go. Let's start here at the Solar and Holospheric Observatory. To search it, you can either go to this website right here. You don't have to memorize the website. You can search SOHO on Google, but I would include NASA as an additional keyword. Otherwise, you're going to get pictures of a neighborhood in New York City. So go SOHO NASA, and you'll go right to this webpage. Well, I gave you, it's current of today. The last picture I show you here is going to be current of today, and what you want to pick is HMI. If you have a solar filter for your telescope, you'll likely have a beta or a white filter for your telescope if it goes on the end of the telescope, and that's what you'll see in a standard white filter. However, they make more sophisticated filters. For instance, an alpha filter will you'll see a more narrow band of the sun, and you get to see other things when you do that. But the standard white filter, pick HMI and you'll see that. And what you'll see is this. And the reason I'm included 3 pictures is this is 2 years ago. This is last year. And this is today. That was actually, I downloaded that today. And you see a trend? More spots. That's a good observation. We'll go into that in a little bit. There's more spots happening. Something is changing on the sun. All right, let's first talk about what's going on the inside of the sun. Here's the materials of construction. So you only need 3 ingredients. So really easy for any of us who want to build a star home. It's only 3 ingredients. Very easy recipe. All right, hydrogen, helium, and metals, various. Okay, so that's a little bit of a red herring, because in astronomy, metals are any element that is not hydrogen or helium. So it's hydrogen, helium, and everything else is what those lines mean. Okay? The Big Bang created mostly hydrogen and some helium. That's why astronomers say hydrogen, helium, and everything else, because most of existence is hydrogen and helium. They are by far the most abundant elements in the universe. And this, in our sun, this is the ratio: 71.54, 27.03, and 1.43. That's not too far off, not that far off from the Big Bang. Here's an analysis of the sun's light. This is uh, a spectrum of the light coming from the sun. Specifically, it's an absorption spectrum. And the absorption spectrum works like this. You see the rainbow colors, all the colors of visible light in this instance. And you see these black lines. So what's happening? What's making those black lines? Well, the sun has an atmosphere. Itself has an atmosphere. This is where it has ions of various elements. What happens is the light comes from the sun, hits that atmosphere, and that light gets absorbed by those gases in the atmosphere. Now, if the sun's over there and I'm standing here looking at the sun, there's a path between the sun and my eyes, and these gas particles are there in the way. However, when those particles, those atoms of gas absorb the light, the electrons will jump from one state to another, and you realize that different outer electrons require different energies to get promoted from one orbital to another. You might remember that from science. And then the light will be re-emitted when that electron changes back from that high energy state back to its normal or lower energy state. And that light gets re-emitted. So why are we getting a black line? If that light is re-emitted, then why is it a black line that we're getting? Why is there a lower concentration of light in that particular energy range? And the reason is because that light isn't necessarily directed at us anymore. That goes off in a random direction, which includes 360 degrees in 2 dimensions. So it's unlikely, so that we see a dip in energy level because that light gets absorbed, but doesn't necessarily go directly to our eyes or to the detector anymore. So that's why we get that black line. That energy is absorbed and then re-emitted, but it isn't necessarily directed at us anymore. So we get a black line. Also, this is the abundance of elements in the sun. Now, you can't see all this because that's a very small graph. But what we see here is you see these 2 points right here. That's hydrogen and helium. Then we see 2 points here that's low and is comparable, say, to these elements over here. This is elements that are low in atomic number, like hydrogen and helium. And these are and these are elements that are high in atomic number, like all those weird metals. And then we have a bunch of elements in this range here that start up relatively high and go down lower and lower till we reach about that same point of these first 2 elements. And you might say, hey, there's something going on there. Why are these more? Why do we have more of these and these 2? And why do we have less of these 2 and these guys? And yes, there is a reason. These 2 were the formation of matter in the first place. That's the Big Bang that hydrogen and helium were formed at. These 2 elements are the same as the background elements of stars, and that has to do with stuff that was formed by catastrophic processes, such as a star blowing up and things like that, very infrequently. And these elements here, which are the more abundant elements in all of nature, are elements that are actually formed in stars. So the bunch of different mechanisms, what you're seeing is different mechanisms of how these elements were formed. And these abundant elements, as I just noted, stars form them. So that's kind of cool. So let's play a game. Here's some specifics about stars and some numbers, but let's try to appreciate those numbers a little bit. The core temperature is 1.56 times 10 to the 7th degrees Kelvin. What's that? Everyone remember what that 10 to the 7th means? Seven times, right, which is something in the 10 millions, right? Right, something in the 10 million. So that's like 15.6 million. Okay, so very hot, right? And a hot day, say on the planet Earth, is what? Death Valley can get 200 degrees. What is it? No, maybe I'm 130, 140, 150, somewhere around there. Death Valley, 140 degrees Fahrenheit. So a lot of extra zeros on the end of that. The core pressure is 1.97 times 10 to the 11th, which is an even bigger number with even more zeros. How many atmospheres are we experiencing right now? Yes, sir. One. Okay, so very different. And even at the bottom of the ocean, it's something in the thousands of degree of atmospheres. So we can't even appreciate that anywhere on Earth. The mass is oh my gosh, 10 to the unnumber times 10 to the 30. Okay, well now we're getting into ridiculous numbers. Even if we divide that into, if we express this in tons, we only get to take 3 zeros off of that 30. So still a ridiculously large number. The diameter is 1,391,400 kilometers. A distance is 1.496 times 10 to the 8th kilometers. In miles, that is 93 million. I just want everyone to do this thought experiment. Who's camping here today? Oops, I'm past the yellow line. Sorry for our folks at home. Anyone camping? Yes. Okay. So have you had a fire yet while you've been here? So if you set a fire and you walk and you go back 10, 15 feet away from the fire, you really can't feel it anymore, right? Yeah, especially on a colder night. All right. So the sun is 93 million miles away from us, a lot bigger than 10 feet. And yet you can turn your face to the sun and you can feel the sun on your face. Just think about how powerful the sun is. A campfire 15 feet away, you can't feel it. The sun 93 million miles away, and you can feel it. That's pretty powerful. All right. That distance is also defined, the Earth-Sun distance is defined as 1 AU. What is an AU in a light year? That's astronomical unit, AU. What is an astronomical unit in light years? That's 0.00016. And I mentioned earlier, Proxima Centauri is 4 light years away. So just so you want to understand the scale of our solar system compared to our galaxy, our nearest star is over here in having a 4, and when our sun is, what is that? That's 1,000. That's a million times, or 4 million times. So that's the nearest star to us. Now just think of all the other stars that are a lot further away. And energy, 3.828 times 10 to the 26th. It's something in the 5,000 times the amount of power that we produce for ourselves. The sun produces for us. So what is inside the sun really? What is the sun actually made of? We talked about its constituents. We talked about some of the facts and figures. So what is it really in words? It's an incredibly hot, incredibly massive, and under gargantuan pressures. Just big numbers all around. It is not made up of matter as we experience it here on Earth. It's made up of a fourth state of matter called plasma. Plasma is mostly made up in our case, but in all stars' cases, mostly of hydrogen atoms, helium nuclei, and free electrons. That's what plasma is. The various nuclei of the atoms are completely stripped from their electrons. So it isn't even an ion anymore. They're just completely disassociated from each other. Plasma is a fluid, even if it's extremely dense at the core of the sun. The average density is 1.41 grams per cubic centimeter, which is weird. That's the average, not at the core, the average density. What is that very similar to? What does that look a lot like? Water. Water is 1 gram per cubic centimeter. So the average density of the sun isn't so big, but the core really, really dense. At the core, it's greater than 10 times the density of lead. Still a fluid, but it's that dense. So here's the solar structure. You have here a core. You have here a radiative zone. The core is, of course, at the center. The radiative zone, where the light travels for a long period of time to reach the convective zone. The convective zone then travels much faster, although it isn't immediate. The light travels to the edge of the sun, or the surface of the sun, and then it radiates and shoots out at the speed of light through vacuum to us once it gets free. This is tens of thousands of years to go through the radiative zone. It's called the free mean path. And if you want to look up more about, I don't want to get too sciencey on you, but just imagine Plinko. You know how you drop a ball, it goes right down to the ground, and this is Plinko on a grand scale, where the light shoots out, but it hits something immediately and goes off in another direction. It Plinkos around for a while. All right, sounding like I dropped out again. Are you still can hear me? Great. All right, sunspots here on the edge of the surface of the sun. The photosphere is the surface of the sun. The chromosphere is that atmosphere where we're getting colors from the and absorption spectrum from the sun. We have a flare here that you should show in a different color, not that white filter that we were. An example of a coronal hole, and then the corona, which is actually rising away from the sun, that we can see during something that we had relatively recently. You can just say it out. Total eclipse. Yes, very good. All right, the sun is a magnetic dynamo. Here's what's happening. The sun, as we said, is a fluid. It is not solid like the Earth is. When Canada and the United States rotate around the Earth, they're still in lockstep with each other on the way around, right? Canada's still north of us when we reach the next day. However, the sun doesn't work that way. It's a fluid. The equator travels much faster than the poles do, and they twist. So what happens when you have charged particles, which is the sun is made out of, free nuclei and free electrons, and they're moving at different speeds, you develop who remembers that from physics? A current and magnetism. And so the sun is actually a magnetic dynamo. So it's making this huge magnetic field, and that magnetic field gets complicated and twisted as those different rates spin past each other. And so you get something that I alluded to earlier, which is the solar cycle. So these complicated magnetic patterns develop over 5.5 years and then calm down again to their resting state for a total of 11-year cycle from one say nadir point to the next nadir point. And the solar cycle is 11 years long from solar minimum to maximum and then back again. And looking at those pictures, if you remember earlier, of the white filter, what do you think we are closer to right now, maximum or minimum? We're at maximum. We're close to maximum starting about now. Scientists, you can't say that was solar maximum until you've actually been through it and you see that it's trending downward, right? So but scientists predict that right about now through 2005 is when our current solar maximum is happening. It was originally discovered by recording the frequency of sunspot activity, but when people back in the old days before they knew better, just, squinted at the sun for a little bit and counted sunspots. Flares, sunspots, coronal mass ejections, and coronal holes and other solar surface and atmosphere phenomenon all vary with the solar cycle. It's important to study and predict these solar events or space weather to protect our infrastructure, our satellites, and of course anyone we happen to be sending up into space. And nowadays we have somebody 24/7 in space, right? So we have someone to be looking after on a constant basis. So solar weather, this solar and understanding the solar cycle is actually an important thing. All right, so that's overview of the internal structure of any star, or our every star in this case. A star is born. Okay, how cute. Please be very quiet for the next couple of slides because we don't want to wake the babies. This is a stellar nursery. You might recognize this one. It's in somebody's belt. It's in Orion, right? This is actually the Great Orion Nebula. Here's the Lagoon Nebula, and I'm sorry I lost the reference for this one, but both are examples of star producing regions of space. Here's some pictures that we have nowadays of sun in the middle there, but these aren't actually just the sun themselves. This is with the protoplanetary disks. That is, you can see spaces around the gas around certain areas around the sun are clearing out, and so that's actually planets being produced around the new stars. Kind of cool. So what is a stellar nursery? A stellar nursery is when a cold, dense, massive nebula, a cloud of gas of molecular hydrogen exists. And then when we say cold, we mean about 10 degrees above absolute zero, minus 273 degrees C. So 10 degrees above that. Massive means tens of light years across. So more than the distance between us and our nearest star. So the gas clouds have to be huge. Protective, so that cloud becomes protective of disruptive cosmic radiation coming from other sources that are everywhere in the universe. Regions can collapse spontaneously if they meet what's called the Jeans mass. If this cloud region meets a certain mass limitation, then the gravity of the cloud itself just starts pulling it together. That's an quiescent or a very still state. Collapse can be assisted by perturbations, disturbances from external events, such as a passing star, nearby energetic event, or cloud collisions. Think of it as a wave. If a wave happens through the cloud, it can sort of nudge the star formation to start happening. Once those conditions are met, a protostar begins to form. What is a protostar? A protostar is a star heated by gravity collapse, but it hasn't ignited in a nuclear manner yet. So it is not fusing anything. However, that expended energy of all that gas coming together starts heating things up. And you know from science that if you move things and they get closer and denser, they're going to get hotter. And that's what's happening on the protostar. Remember of conservation of energy. It's the law. It's that potential energy that we are expending of that gas collapse that is getting converted into heat energy. Potential energy gets converted. Kinetic energy, that is what heat is kinetic energy. Kinetic energy increases. Enthalpy, there's a thermodynamic reason we call it enthalpy, and we won't get into that. But heat energy and pressure energy combined there increases. And if the protostar is massive enough, eventually hydrogen fusion or burning can be sustained. So it has to reach a pretty high ignition temperature for that fusion. And once that starts happening, then the hydrogen fusion can be sustained. The collapse is halted once that lights off like that. Hydrostatic equilibrium is reached when that happens, and then a new star is burned. So once it actually lights off that fusion process, that's when it's no longer a protostar from collapse, but a sustainable star. Two opposing titans. Hydrostatic equilibrium is two opposing titans. There is the gravity collapse. Gravity didn't disappear. It's still trying to pull the star in. However, there's now a counterbalancing force. The plasma pressure of the fusion happening pushes out on the star, and the star reaches a hydrostatic equilibrium, where the two forces are equal, pulling and pushing the star into its final size. And that's not necessarily true that it's stable. It doesn't hit just one size. Why is it stable? Well, remember, a collapsing fluid heats and an expanding fluid cools. Changes in the rate of fusion are opposed by changes in the plasma expansion. So if you increase, or say you the star happens to collapse a little bit, it isn't perfectly stable, right? Say it happens to go through whatever it went through and makes it collapse a little bit. The fusion, because it gets a little bit hotter and denser, the fusion gets kicked up a notch and pushes it back out again. So in that way, you have this self-stabilizing system where a change is resisted by an opposing change in the system. All right, powering a star. So we talked a little bit about fusion and how it halts gravity. So what is this fusion thing? Sometimes fusion makes sense, and it's easily to understand if you've looked at the science a little bit. And this is the Maxwell-Boltzmann distribution, and this is just if everyone's familiar with the bell curve? Okay, well, this probability curve happens when you're bound on one side. And in our case, we know that that it's probably unlikely that, or we know it's unlikely, we define it as unlikely, that zero atoms in the sun will have zero energy. So we can say 0, 0 here, right at the origin of these axes, is going to be a bound point on this distribution. And so this is the distribution we get, what a bell curve ends up looking like when we bind it on one side. That's all this is. This area in blue is where we've just used a general activation energy point. We don't have a number here on this curve, but that's all right. It's just an illustration. It's just saying everything to the right of this point here, that has enough energy to collide, for two atoms to collide and cause fusion. That's all we're saying here. And that would make a lot of sense if that's how it worked. But it doesn't. Sometimes it's a head scratcher. So they actually did a test, and that the electro forces of charged particles charged particles trying to collide together is actually the force that you would need to ram those two things together is actually much higher than the activation energy that nuclear fusion happens at. So there's something else going on. And what's going on? The electrostatic repulsion of the like-charged particles, I just said that. It's like I've given this presentation before. However, the smallest of matter is quite weird. They can behave like waves. In other words, what's going on is particle physics. Small particles can change position without moving through space. They quote unquote teleport. They don't really teleport. It's a quantum physics thing. It doesn't have to do with magic, okay? But they teleport into the new nuclei. The higher kinetic energy a particle has, the more likely it is to tunnel. Quantum tunnel is what this phenomenon is called. And the quantum tunneling is required to make fusion go. The activation energy is too low. In order for us to have a sun, this quantum tunneling, this what I said isn't magic, but appears on the outside as magic, of it teleporting from traveling through space without going through the intervening space, is real. We know it's real because it's happening in our sun, and that's the only reason the sun can exist the way it does. Remember, what is fusion doing for us from an energy point of view? Remember, E equals mc squared. Matter is a form of energy. It is not different from energy. It is a form of energy. There's an equivalency, and some famous guy, I forget his name, E equals mc squared, you guys remember? Albert Einstein, E equals mc squared. That is the equivalency. So that is not telling us just some mathematical, theoretical thing. That's actually telling us that energy and mass are the same thing. 700 million metric tons of hydrogen is converted to helium per second by the sun. 700 million metric tons of hydrogen is converted to the helium per second by the sun. 5 million metric tons of matter gets converted to energy per second in the sun. Now that sounds like a lot, and why do we still have a sun if that amount of material is getting cooked away all the time, right? Well, here is why. Remember those big numbers? This is why those big numbers are important, because the sun is 2 times 10 to the 27th metric tons. This is only 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces, yet we still have almost, what's that number? Over a trillion tons times that. I mean, a trillion times that of material to burn. All right, so that's why those numbers become important to understand, right? It's not just fun with big numbers. That's why they're important to understanding what's going on. The reason why this insane amount of material getting fused and getting disappeared into energy doesn't translates to the long lifetime of our sun, 7 billion years, or it's 4.5 billion years now, but what is it, 10 billion years, something like that. I forget exactly how long it is. 10 billion years, but that's why. Here, take this amount of number, start 4.6 billion years ago, and do the multiplication, and you can figure out something about how long our sun's expected to last. Here it is. There's enough material to go on for about another 7 billion years. Okay, so our sun's going to last a long time, even at that insane conversion rate, because it's so huge. All right, and I found this, as a chemical engineer, I find mechanisms extraordinarily interesting. I put it up there for you guys. Just see that it doesn't happen all as hydrogen hits hydrogen and makes helium. There's a little bit more to it. Here are the actual steps. Here is a positron. Oops. Here's a positron being given off, and here is whatchamacallit, I'm forgetting the name of it. I'll come back to it. But here's light being given off. I'm sorry. I'm forgetting the terminology. Neutrino. There we go. Electron neutrino being given off, and two helium. 3 atoms eventually combine to an actual helium-4, our standard helium, plus a hydrogen proton. So it's more than one step, and that's for a sun our size. Actually, here's where a major difference between our suns and other suns are in the cosmos. Larger stars, instead of using this proton-proton chain, use this chain, which actually, if you can see, requires some intermediary atoms. So you can't just have pure hydrogen and have this cycle, because it needs intermediary steps. That's not to say this doesn't happen in large stars also. This is just the preferred mechanism once the suns get that large. A little arithmetic. Atomic weight of hydrogen is about 1 gram per mole. Atomic weight of helium is about 4 grams of mole. 4 times 1 hydrogen equals this number. And if you compare this number to this number, you'll notice that there is this amount of weight missing. Okay, so that small amount of weight missing between the conversion of hydrogen to helium is what is getting converted to energy and what makes the sun what it is. That's the fusion. That matter, that difference, is what's getting converted to energy. Our sun has class. Where do we fit in? What we can't know about it, we cannot know the size of stars or their luminosity from knowing their brightness by itself. Light's brightness depends upon its distance from us, so it has an inverse square relationship. So is that a bright star that is far away or a dim star that is close to us? How do we know? Just by looking at it. Stars' brightness can be classified by their magnitude. We call it magnitude in astronomy speak. Stars' luminosities can be classified by a unit of power like watts or absolute magnitude. that an absolute magnitude is just the same concept of magnitude, except in order to make it, to fix it, fix that number for individual stars, they just said we arbitrarily choose 10 parsecs away from that star, and now that is the absolute magnitude. Since we all are the same distance from every star, at least according to that measurement, now we can say that that is a measurement of the star and not a membership of the measurement of the distance between us and the star and its brightness at the same time. What we can know is that black bodies of stars are approximately black bodies, irradiate with color intensities with a predictable curve. Knowing the curve shape, color index, we can predict the surface temperature of the star. Knowing the surface temperature, spectral type, and luminosity class, and a whole other lot of physics, we can know the star's masses. And knowing a star's mass let us know many things about a star. So by studying the sun and studying nearby stars, we related our knowledge of how close they are and the light coming from them to be able to classify stars, to know what their output and their size is. Because we solved that equation. We solved the two unknown equation. We solved the brightness because we knew the distance. And then we related that to the light that's coming from those stars. It turns out they're directly related. So remember our the sun spectra. We saw this. We know it's what's the light coming from it. We could classify the star and its spectra. And classifying the star and its spectra, we took knowledge of science and the black body radiation curve, and we could start relating stars. This is our star here. You notice the peak is in the green. That's our star. That peak is in the green, and we related that star to its size, and we know stars follow this curve. So here's the various classes. Based on these spectra, we learned these spectra of the stars first before we got the physics down. A class of stars here. We show the lines of those spectra. Remember these absorption lines we talked about. There's the dominant lines there for those various spectra. The colors of the star, we rated that color in a color index, and then we calculated the surface temperature of those stars that the physics produces. It says that we produce. So we related the size of the star, because we know that the outside temperature is related to the mass of the star. We've related that outside temperature, the color that's coming off of those stars, to its size. And then we put it on, hold on. Here's various stars that you may have heard of. Betelgeuse is one you've probably heard of. Rigel, Polaris, the North Star, Aldebaran, Vega, Sirius, the Sun. These are their luminosities, their mass, their radius, and their temperatures. The suns are all one because we use that as our reference. And here's the diagram. This is called the Hertzsprung-Russell diagram, or HR diagram. The sun's right about here, right, I think a little left of center. And these stars are all on what's called this, you see all these data points and how fuzzy it is? That's all, oops. That fuzziness is all individual stars plotted on this diagram. The main sequences: hydrogen burning. The sun is G2, class 5 at almost 6,000 degrees Kelvin. And I just want to show you up here that these are supergiants and red giants up here, and these are white dwarfs down here. And this sequence that you see, all these fuzzy data points are a lot of stars. And so this HR diagram, where 6,000, like I said, a little bit left of center, is about where the sun is, right about there. I bid adieu, so do the stars eventually. What happens to them? When the sun uses up its hydrogen fuel, it will collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. More massive stars will repeat this process, so not only will it go from carbon and oxygen, it will continue on producing neon, manganese, silicon, and these are all concentric active cores found in massive stars. So all this is happening at the same time. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand and become a red giant or a red supergiant. Regardless of mass, because this is independent of mass, fusion stops at iron. Iron fusion does not happen. Iron fusion is endothermic, to put it in chemical terms. I don't know what you call it for nuclear terms, but it takes more energy than it produces, so it kills the reactions because you can't feed it enough energy for it to go unless you have an external source. Once fusion stops, hydrostatic equilibrium that we talked about disappears. The sun or star will continue to collapse until something stops it. So what besides fusion will stop the gravity collapse of a star? Electron degeneracy holds up white dwarfs. Like particles, two electrons don't like to be near each other. Particles with quantum value like quantum values must stay separate. Pauli exclusion principle. The free electrons, such as a star, order themselves and provide a back pressure to resist gravity. Two electrons have to achieve two different quantum numbers, and they align themselves to make that happen in a huge like matrix. So that stops the star from collapsing, that electron degeneracy. If the electron degeneracy isn't sufficient, in other words, if the gravity pull, if the star is massive enough, if the gravity pull is too much for electron degeneracy to stop it, it takes about 1.5 solar mass of leftover star for this to happen, the star continues to collapse. Neutron degeneracy then holds up the neutron stars. So when I say the Pauli exclusion principle, it's the same for all particles, except that the neutron degeneracy has an assist because it's a baryonic matter. It's a neutron instead of a electron. That neutron, since it's baryonic matter, the strong force comes into play, and the strong force adds its strength to the previous Pauli exclusion principle, and it gives an assist, and so the star can stop there because that strong force is providing additional support to push gravity back. Neutrons are excluded from occupying the like states. The neutrons, stars get an additional assist from the strong force. And beyond these two forces, in other words, if the gravity is too much for even the strong force and the Pauli exclusion principle to resist it, I don't know of anything else that will stop the collapse of the collapse of that star, the continuing collapse of that star. And turns out neither does the entirety of physics. What happens is that that star remnant will continue to collapse and will form a black hole. And I am going to leave that there. I have a black hole presentation in development. Do not go gentle into that good night. This is the Ring Nebula, and this is the Crab Nebula. In the center of the Ring Nebula here is a white dwarf. In the center of the Crab Nebula is a neutron star. Okay, everyone, join an astronomy club, please. Stay safe, And thank you for listening to that presentation on stars. And I think we're going to go into Q&A next.
You would be correct. Thank you, Paul, for another great talk. Now, before we get into Q&A, because I know a number of you snuck in during the presentation and missed the safety briefing, and there is no escaping the safety briefing because I have declared it so. If you need to use the restroom, that is the porta potty to the back. It's illuminated by red, so you can find it easily in the dark. After the presentation, I will also be manning the little museum and gift shop area, so feel free to check that out. Uh, Inside each of those sheds with the roll-off roof is a telescope, and one of our volunteers operating it. Feel free to ask them what they're viewing, and or if there's a target you have in mind, ask them if it would be possible to currently view that. When we go to leave, chances are it will be darker than this. Therefore, we are using headlights. That is right. We want you to use your headlights because we do not want to get run over. And I'm sure you feel the same way. It's way too much paperwork. However, if we are wandering around with flashlights, do be mindful and keep those pointed towards the ground because we don't want to be randomly blinded by a flashlight out of nowhere. With that, how Q&A is going to work is you're going to raise your hand and wave it about like you don't care and wait till I bring you the microphone, because if you have that question, someone online probably has the same question but might be too shy to ask it, or someone here might be too shy to ask it. We're going to start off with the first online question. Because online chat, you have the easy thing, you can just type it in. The first question was, is it possible to have a star without its own system of planets and debris?
I imagine it is, although identifying that might be problematic, because are you not seeing the planets because they aren't there, or are you just not seeing the planets? So I imagine it's possible, but I imagine it's also unlikely. But you're going to have to look that one up itself. I don't know whether they know. That's an excellent question, and I don't know whether we have identified suns that had not developed a planetary system with them. Of course,
Schrodinger's planets, they're both there and not until you finally find out.
until you find that's Schrodinger's planet. The other thing is to remember that solar systems have a history associated with them. So is it that the star you're currently viewing that doesn't seem to have any planets, did it not develop them? Or were they later stripped from the solar system by interactions with another star? And certainly with complex star systems that have multiple stars in them, the likelihood that a planet just gets ejected from the gravitational interactions between the stars is much higher. So I don't know whether we've ever identified a star that we knew developed without planets.
All right. Did you have a question in the back, sir, or are you just doing calisthenics? Bug. There was a spider. I did not like that. Oh, we do have a question here.
Is it called nuclear fission, not nuclear fusion?
No.
When sun is like forming, so.
When the sun is forming, no, that's actually just thermodynamic heat from the conversion of potential energy into kinetic energy. So in that protostar phase, that is a thermodynamic conversion of energies. And as it doesn't have that fusion associated with it, it might start lighting off occasional fusion, but it's not sustained fusion, and it is not fission that is happening, it is fusion. So you're taking smaller atoms and you're making larger atoms out of them, and therefore it is fusion, not fission.
All right. So our next online question: how would we figure out the habitable zone of a star much larger or much smaller than ours?
Uh, by the energy output. So if we saw those various spectra, etc. So you know and I just got hit by one of those spiders. If you know the classification of those stars and you can classify its light and know how big it is and how much energy it's putting out, therefore, then you know the theoretical habitable zone around that star. Now, star stability and all those other factors come into play. Is one reason why they think that they originally thought that maybe red dwarf stars, which are the most abundant stars in the universe, might be a place where we could find alien life. And then they did a little bit of an about face on that because they further study. They've realized that red dwarfs aren't as stable as, say, our sun is, and therefore that sun's variability would not do good things to things that are trying to live around that star. So that habitable zone is theoretical, I believe, based on the classification of star that it is.
All right. Another question over here.
How big is a red giant?
How big is a red giant?
Wow, I don't know how big a red giant is off of the top of my head, but let me tell you this. When our star goes into that red giant phase, it will the star will get bigger than the orbit of our planet. So that's not good news for anyone who might be around in 7 billion years or so. It certainly won't be us, and we might not even exist anymore as human beings 7 billion years from now. It might be somebody else, might be some other version of a human sitting around worried about that.
We'll have graduated from human beings to human bean plants.
Something will probably have happened in those billions of years that we don't really have to worry about it, but they get very big, right? It's 93 million miles away, and that our star might be big enough to encompass our orbit.
I know Betelgeuse is very big, and it's dwarfed by, I believe it's Antares.
There are a bunch of stars, and there's even stars with like weird number letter combinations that are much bigger.
Variation. I saw another question over here.
Excuse me, I just wanted to ask you, like, is this the question? I mean, I don't know whether it is. So that we have heard like there's a death of the stars. Stars die every year. So is that the myth or is it the real thing?
Is the star actually dying a myth,
Yeah,
or is
dying,
it real?
yeah.
So remember what I said about the advantage of not only that our understanding of stars is a model in our heads, and our advantage of being close to our sun, as well as having the ability to look up in the night sky and see all the distant stars we can see, is that we have gotten to witness, and even astronomers in the Far East, and I imagine in all areas of the Earth, but we have the records from astronomers in the Far East, and in some of the Arabic texts also, have witnessed supernovas in the sky. So we've actually, as human beings, have been witnessing the death of stars for thousands of years. That's not just a modern invention on our part. We've witnessed supernovas for thousands of years. So we know pretty reliably that the stars do have an end date. But like I said, ours is 7 billion years away. That's not something we have to worry about. So that's not, we all as human beings have to live with a certain amount of cognitive dissonance. That's not something that we should even put on our radar as something we need to worry about.
day there's a day, every star, one or the other star keeps dying.
Oh, so the fact that there's 0.3 trillion stars in our own galaxy, it's probably happening every day in our galaxy, much less the rest of the cosmos. So it happens on a frequent basis, but just like human beings, there's still stars being formed here in our galaxy too. Not as much as there used to be. Our galaxy is pretty quiet compared to what other galaxies are, but so similar to humans, there's a beginning and there is an end.
Right. So our next online question is there any correlation between how solar systems exist and how the model of an atom is, where like the nucleus equals the sun, the electrons equals the planets and other orbiting bodies?
On the surface, it appears, and certainly there are some spatial things going on that might be similar. However, the physics are very different. Atoms are governed by particle physics, where solar systems are governed by Newtonian physics. So the answer is physics in general control both, but they're actually two different, pretty different animals when you get down to the details of it.
Hello.
Yes, sir.
So, but you said earlier, which I found interesting, was that um, the equator of the sun travels faster than the poles.
Yes.
So I was wondering, like, when it's twisting and turning, does that have an effect on the gravitational pull on other surrounding planets?
I don't. The sun is not quite a. Can I ask where you are in your, say, journey through physics as I assume a student?
So I'll be taking AP physics next year, but I'm taking honors chem now.
You're taking honor
Chemistry, yeah.
chemistry. So you'll get into this mathematics, especially if you continue on in some sort of science or math in after you graduate. However, the sun is basically a point source to us, which defines a certain geometry to the mathematics associated with the fact that it is a point source, that it's all in one location and not a plane and not all around us. It's all coming from a point in the sky. And so the fact that it's all coming from that direction anyway sort of negates the fact that if you were really close to the sun, I would say maybe you have something there, but then you would have to do the math to figure out whether that's a significant change or not, depending upon where you are close to the sun. So, good question, and come back to me when I give the presentation on black holes, because as it becomes a true point source, even more interesting geometrical gravitation effects occur. So that's a good question.
All right, so our next online question: how close can a human travel to the sun before there is too much heat or too much radiation where it becomes, and I quote, too hostile to life as we know it?
Yeah. I don't know the exact answer to that, but believe it or not, other factors come into play. Your ability to what you happen to stand on to cool, for instance. And here's an interesting fact. So you'd have to look up that actual number where if you're just existing in space where you couldn't take the radiation coming off from the sun. We do know that, for instance, astronauts who went to the moon were experiencing very hot temperatures when the sun was just beating down on them without the ability of an atmosphere to help with some of that heat, to shield the astronauts from some of that heat. But an interesting fact is that Venus is actually hotter. The surface of Venus is actually hotter than Mercury, yet Mercury is closer to the sun. And that has to do with the ability of Venus to cool off because of the thermal runaway that is happening on Venus. Venus can't cool off like Mercury can cool off, and radiate heat back out into space. So Venus, we would have difficulty existing on both of those planets, but Venus we would actually melts lead. So don't be on Venus, and it's actually the second closest planet to the sun. So that's a so there's other factors involved too.
All right, we got a question here.
Um, was our sun always as bright as it is now?
Oh, that's a great question. And the sun is actually heating up just a little bit over millions and millions of years. So some people might be tempted to use that, say, in a political argument, and we won't go into that at all. However, the sun is actually heating up just a little bit as it gets older. So no, it wasn't always the same temperature. But this effect is very small, and it happens over millions of years, not anything that we would experience as modern human beings who have been around for less than 1,000,000 years.
All right, online chat, do keep getting those questions in. I don't want to miss any questions after we've gone offline, but if you do happen to get a question after we've gone offline, do still put it in the comments, because I will try and get to those when I review the YouTube comments later. All right, I know this.
Hi.
Hi.
What causes a star to go supernova, and what happens when it does?
So yes, a number of things can happen with a star going supernova. Let's just talk about the end of life death of a star. And what happens there is that star, remember, it has to be, the remnant of that star has to be massive enough that even neutron degeneracy pressure is not sufficient to resist gravity. So it has to be that in order for it to be collapse into a black hole. The thing that the precipitating event is the fact that it has reached the successions of cores. So it went through oxygen, carbon, it continued on through manganese, silicon, and then so those cores form as the temperature inside that core increases, because the star is starting to collapse and get hotter and hotter. Those fusion cores form in successive layers, and then it reaches and it suddenly stops. Iron, because iron takes energy, doesn't give energy. So there's no longer energy flowing out of the star. The fusion is all going into forming that iron, and so the star just collapses. The gravity is nothing to resist it anymore, so it just collapses the star, and then boom, supernova.
All right, so the next online question is, what happens if you do, quote unquote, wake up the baby star?
Wake up the baby star, the protostars, that's when the fusion. So if you remember the end of that slide, I said that that increasing conversion of potential energy into kinetic energy allows the core to get hot enough that fusion starts. And once the fusion starts, it stops the gravitational collapse of the star, and so a stable environment is formed because you have that fusion counterbalancing the gravity, and therefore it maintains that state for very long periods of time.
All right, we got a question here.
Are we trying to find a planet with life on it, or do we have a planet with life on it that is not in our galaxy?
I think we have suspected places in in our neighborhood, including stars, but including some moons in our own solar system, where we think there is a possibility of life. and we are using various investigative methods. And when I say we, I'm not doing any of this. Scientists who are expert in this field are looking at the spectra, the light coming from it, trying to identify atoms and molecules that life produces, as opposed to naturally occurring in various planetary systems. So various forms of chirality, various shapes of molecules, I should say, that life produces. And also, in our own solar system, we can actually send probes to those places and try to investigate by taking samples of that area. So not only are we doing it through light, but we're also trying to check it out physically in our own neck of the woods. Good question.
All right. So our next online question is, wouldn't the mass of the star change by individual ratios of material making up that star? How do we know the material and approximately how much of that material is there? And they gave a clarifying statement, kind of like there's multiple ways to make $1 worth of change.
That's a good question, but remember that using that spectra, we can actually now analyze what is in the atmosphere of that star. So, and we also know that the predominance of matter in the universe, and when I say predominance, I mean the most matter, huge amounts, like 98% of matter is helium and hydrogen. So that's a gimme that stars are made of helium and hydrogen. Now, the older a star is, it's the more pure helium and hydrogen it's theorized it is. So they're always looking for what they call primordial stars that have very low metal content. So other stuff in it. So they're always looking for those that generation of stars that maybe came from the Big Bang. They're looking for those things, but they're always analyzing that light coming from it, because again, we can see what that atmosphere around that sun is actually made from the spectra we get from those stars, because that's very specific atoms making those very specific patterns of black lines.
All right, we got another question here.
Are all stars formed in stellar nurseries?
I imagine there are scenarios where they're not. For instance, right after the Big Bang, maybe they just formed just by being there. However, I'm not a physicist to be able to answer that question directly, nor do I have nor have I read an answer that there is some sort of other mechanism for star formation. But I think it's a pretty good, considering that's where I've read most of where new stars are coming from those deep nebulae that we can see through and actually see that star formation happening. I can say that that's what my knowledge, limited knowledge, but an expert in the field might be able to tell you that there is this other possible mechanism that stars can be formed by, but I'm not aware of one.
All right, were there any more questions out here? All right, so I have one last smart aleck comment from chat.
Okay.
And it is a little bit of a spelling pun.
Okay.
The Paul -E, the Pauli exclusion principle. When Paul forgets the math and moves on to keep the flow.
Well, I do, yes. I don't, of course, I'm a chemical engineer, but I went to school a lot of years ago.
A time ago.
Approaching 40 years ago. It's not quite there yet, but so yeah, some of the math has slipped out of the old noggin, and I could probably look it up and understand it again, but I haven't had a call to do it. So yeah, some of that stuff isn't at hand for me to quote immediately.
I think they were just poking fun.
I imagine they were, but me being an engineer had to take it, way too serious.
Because the previous comment was that they really loved your presentation, and it's obvious that you do a lot of research to.
Thank you very much. I appreciate it.
Anyhow, since it looks like that's the last of our questions, I want to thank everyone who's joined us here. Like I said, do check us out on our website, uacnj.org, and our social media, our Facebook, our Instagram, and our Discord channel. Do hit those like and subscribe if you're here for our Twitter or not Twitter, Twitch and YouTube channels. And with that, have a good night, clear skies, and good seeing.
Thank you.